Yeah, so that's what it is.
Okay, so
Anyway.
should we start? I've admitted people.
Yeah, sure. Let me just close the door. Hang on.
Yeah.
Okay.
So, mute
Right.
myself.
So usually if we have co-authors, we ask them to answer questions in the chat box.
Right.
But it's okay, I will ask everyone to ask as they go along.
No, yeah, I think that should be fine. No problem at all. I mean, yeah, feel free to ask questions. That's no big deal. So let me make sure I have the time.
Yeah. Okay, so we are very happy to have Rene Saran from University of Cincinnati. So there's a significant time difference and still he has agreed to give the talk early in the morning. So thank you, Rene. And the title of the talk is Monopolistic Screening with Single Peak Preferences. Okay, 75 minutes.
All right. Thank you so much, Debashish. It is obviously a great pleasure to be giving this talk. Of course, I would have preferred to be there in person. I lovingly recall the wonderful visits I've had at ISI Delhi. But given the circumstances, we'll have to make do with this. But in any case, I'm delighted to have this opportunity to share my work with you all. As Debashish mentioned, this is title of the work is Monopolistic Screening with Single Peak Preferences. Please feel free to interrupt me. This is a small enough group, so we can have a more interactive session rather than me just talking for 75 minutes. Okay, so let's go. Well, all right, I want to go on. Come on. Just a second. Why isn't it going down to page? Okay. Mouse. Okay. So I'd have to switch to mouse. All right. So let's go on and recall the monopolistic screening model first, since that's the key phrase in the title. What I'm considering is a model with a single principal and a single agent, where the agent's type is her private information. The principal's payoff is a function of both the agent's type as well as the action taken by the agent. So there is this asymmetric information. Principal doesn't know the agent's type, which is because it's a private information of the agent. Okay. So what does the principal do in order to overcome this asymmetric information? The principal typically will design a mechanism or a contract which will screen or distinguish different types of the agent. And how does he do that? He does that by offering a contract which is actually a menu of options. Okay, so it's not a singleton, but it has multiple choices. And when two different types of the agent choose two different options, then the principal is able to distinguish between those two fellows, right? So now, the key thing which is there in standard screening models is that each option in the menu is typically a pair, right? Which specifies both the action that the agent must undertake and the corresponding transfer payment, either to or from the agent that will be obtained, right, when the agent takes that action. So it's typically a pair, an action and a transfer payment. So now let's look at a slight variation of this model, okay, where suppose that this monopoly is regulated so that it is going to only charge a fixed price. Okay. So before that, let's simplify stuff a little bit, and concretize things a little bit. So suppose you have this monopoly which is producing a single good at a constant marginal cost. So let's take the simplest possible model. The buyer's demand is linear. So it is theta minus Q, where theta is her private information, okay? And P and Q are the prices. So on the right-hand side over here, you can see the demand function is nice and linear demand function over here. Okay, theta is the private information of the buyer, and let's assume that it's uniformly distributed. Okay, so what's the buyer's utility? What's the buyer's utility in this case is equal to the consumer surplus. So what this model that I'm talking about, by the way, is from Maskin and Riley 1984. Okay, so buyer's utility is equal to a consumer surplus. In this context, what is the consumer surplus equal to? Well, if the buyer purchases Q units from the monopolist, then the aggregate surplus of the buyer is the area below the demand curve, right, up until quantity Q. So this whole, I guess, trapezoid is the right way to call this. And in the standard model, if the associated transfer payment from the buyer was equal to this particular T, then we will take away that transfer payment, subtract that from the aggregate surplus, and what would remain is the consumer surplus, right, which is the shaded blue area. So that's the consumer surplus in the standard model when the buyer purchases Q units, and the transfer payment corresponding to those two units, Q units, is equal to this T. Okay, and on the left hand side here, you can see the mathematical formulation for that consumer surplus. I don't want you to remember this, but just note that basically it is. You can think of this as the first two expressions are the aggregate surplus, that's the area below the demand curve up to quantity Q, and from that you're subtracting this transfer payment. Okay, so in a standard model where you had a menu of options where each option was quantity and transfer payment, and if the buyer were to select one of those options, then this would be the buyer's utility, right? Some aggregate surplus minus the transfer payment. Now let's go back to a model with where the monopoly is restricted. Recall I basically said that suppose the monopoly is restricted to a particular fixed price. In this case, the buyer's utility will be given by this function. So suppose the monopoly is regulated so that it must charge a fixed price of P bar. In this case, the buyer's utility will be, again, if you recall the expression, the first two expressions over here are the aggregate surplus. Then you have minus the transfer payments. Since the transfer payment is simply the fixed price per unit multiplied by the quantity purchased, this will be the new transfer payment, P bar minus P bar times Q. And so the buyer's utility, if you just do a little bit of algebra, is equal to this expression over here, which happens to be single peaked. Okay, so if the monopoly is regulated, the buyer's preferences are going to be single peaked. Now, what difference does this make from a situation where you can have allow the monopoly to charge any transfer payment versus a situation where the monopoly is regulated and only can charge a fixed price? To understand this difference, let me go back and recall the optimal mechanism or optimal contract under the situation where we are looking at, where we have the linear demand curve and the buyer's utility is buyer's type is uniformly distributed. Maskin and Riley provide the result over there. The optimal contract is going to look like this. This is the quantity schedule, and T theta is the transfer schedule corresponding to that. You don't have to remember this, just look at the picture on the right hand side. The quantity schedule basically is such that the monopolist excludes all types below half, and the other types are offered this, choose this quantity as given by the Q theta function. Interesting thing to notice about this function, quantity schedule, is that it's basically monotonic. It's weekly increasing. Okay, and in fact, Maskin and Riley show that you can take any weekly increasing quantity schedule and implement that. And by that I mean that you can provide corresponding transfer payments such that the quantity schedule and the corresponding transfer payments are both incentive compatible and individually rational. So you give me any such weekly increasing quantity schedule, I can implement that by designing appropriate transfer payments. Okay, so that's the result when there are no restrictions on the monopolist. But now let's go back to the situation where the monopolist is restricted to charge a fixed price. Again, as I recall, I just mentioned that in that case, the buyer's utility is actually single peaked over the space of quantities. And now the buyer doesn't have two instruments, right? In the standard model, the buyer offers a quantity schedule and a corresponding transfer schedule. That is a menu of options where each option is a quantity and a transfer payment in order to screen individuals. Now the buyer only has one instrument, which is the quantity, to screen different types of the agent. Okay, so naturally the question over here is now, what do the screening contracts or mechanisms look like? What kind of quantity schedules can the monopolist implement in this scenario? Because the transfer payments cannot be the transfer payments are exogenous, cannot be carefully designed, right? And given those class of screening contracts that the monopolist can implement, which one is the optimal one? All right, so that's the question, kind of questions. Those are the kind of questions I'm going to be tackling in this paper. Let me give you another example, which is actually how I started thinking about. Yes, yeah,
Rene, can I just ask a question?
Yes.
There's just stupidity, I think, on my part. But when this is single peak, but
Yes.
in the standard single peak thing, you have the thetas or something, right? I mean, you would have, am I not right? I mean, you would have an, yeah. So I'm just saying that is this in the right space, or is this equivalent? They're in the revelation thing that you would reveal your theta and it's sort of single peak with respect to that, right? You have an optimal theta, and the further you are away from it, so you've transformed it into quantity space. I mean, I guess it's all fine, right? I mean, it's the same thing.
Right. So the way I'm the way I'm viewing is that of course there will be some assumptions about how the utility function behaves as I vary theta, right? So those assumptions are going to come up. Right now, this is only talking about a single type whose type happens to be theta, and his preferences over the actions, or in this case, the quantities, right, that he can purchase.
That when you have single peakedness, when you refer to single peakedness, it's usually, where you have quantity there, it could be, type or something like that, right? I mean, rather, that's the only thing I was.
Okay. Yeah, I mean, I'm sorry, I'm not sure about that part. I'll have to check. But here, yeah, I mean, maybe that's the most standard thing in perhaps in social choice. Here, I mean, the way I'm for me, single peakedness will always be over the space of actions, right? That the particular agent is can take. So. And this is something which is fairly typical of, and what I want to convey here is that this is fairly typical of these models, where if you go from the standard model where you have a contract being a pair of actions and transfer payments, moment you fix the transfer payments and make them exogenous, you will typically get that the agent's utility function will be single peaked, or I mean, if that's perhaps, hopefully that's the right terminology I'm using. But again, what I mean is it will have this inverted U shape, right? They will, because once the transfer payments are fixed, you're going to be thinking about the benefits and costs associated with taking that action, right? And if you do want to do any interesting analysis, they should be regions over which the benefits is above the cost, and there are regions over which it's the other way around. Okay, so I mean, if this was all nice and monotonic over the space of quantities, then really I don't have much to say. Because you can't screen types when everybody's preferences are monotonic. Apart from in the general model, yes, I'm just going to assume this single peakedness over the space of actions. But here, my purpose is to convey that that's something which comes out in most of these models if you were to fix the transfer payment. So yeah, it's single peaked over the space of quantities. How the utility function changes as we change theta, is something I'm going to discuss later on. It will have the standard assumptions, I
Okay.
mean, single crossing and
Can
stuff
I
like that.
add some comment
Yeah.
on this two
Yeah.
lines? So first,
Yeah.
you're fixing a theta and seeing how
Yeah.
the function looks like as you change
Yes.
view, which is single peak. Fair enough.
Yes.
So, but the point is, I think if you have an incentive compatible contract,
Yes.
then as theta changes, the U
Yeah.
would be convex and increasing, right?
You would be, yes. So if theta was, so suppose if I have to draw a picture of, let's say, what is the utility function of a type which is greater than theta, you can imagine, maybe I have it somewhere
No,
written
that's
down
okay.
there.
That's okay. We can
You can
come back to
imagine
it.
a curve which is something like this. Okay, so good thing is I have this pen. So right, I can now use this pen. So you can imagine a curve which will look, oh no, I don't want to erase, come on.
That's okay. We can come back to it. This is with respect to incentive compatibility. We can come back to it.
Yeah, so I'm going to come to the incentive compatibility. So the curve will, I mean, the utility function of the other person. Oh, sorry, it's drawing pretty badly. It's going to be something like that. Okay, it's going to be above that and to the sort of. It will be above this U-shaped curve, but to the slightly shifted to the right. Okay, so that's one possible utility function of a type greater than theta. Okay. Okay, so I'm going to come to incentive compatibility. That will be imposed, of course. Okay, so next let's look at another example, and this is how I started thinking about this, which is the example with of charities. So when I started thinking about this, what I was looking at was these donation websites and these situations where charities ask people to volunteer. And I wanted to understand what is the structure of the contracts that they actually offer in these situations. I guess typically for volunteering, nobody offers a contract. They just say, okay, you can come in whenever you feel like. So people choose whatever is the optimal effort for the charity. But why is that optimal from the perspective of the charity? That's the question I had. So imagine a charity which is soliciting these individuals as volunteers, okay? And the individual is going to enjoy, I'm going to look at a warm glow model of charity, which is basically that when a person volunteers for these activities, let's say in a soup kitchen or somewhere else, the person basically volunteers because that makes him or her feel good about himself, right? So you're not doing it necessarily for some broad altruistic motives or social prestige motives. You're just doing it because you feel good, right? That you're doing something good for somebody else. So in that respect, I mean, so there is the model is basically by Andreoni in 1989 and 1990. So when individual of type theta is going to exert some A units of effort, the utility of this individual is going to be made out of benefit and cost. So A square over here is the cost of exerting A units of effort for charity. And V theta multiplied by A, this is the aggregate benefit of exerting A units of effort when your type happens to be theta, okay? And so you can think of V theta is the marginal benefit of effort, right? So again, when you look at this model and you draw these, fix the type, yeah, that's important, yeah, fix the type, and you draw the agent's utility over the space of actions, then again, this fellow is obviously nice and single peaked over the space of actions, right? So here I presume charity's aim is usually to maximize the amount of effort exerted by the individual, but the charity cannot offer transfer payments, right? They don't usually pay you money for volunteering. It's free activity. So the only thing charity has in order to screen types of the agent is basically an effort schedule. So what kind of effort schedules or contracts can the charity offer in this situation, and which of those is going to be optimal? Okay. So here is another example where, again, I think thinking about this problem is important. There are some other examples I mentioned in the paper, but hopefully by the end of the talk, I'll give you some illustrate you some show you pretty pictures, I guess, and illustrate the different types of mechanisms that can be implemented in this scenario. Okay. All right. So now, so the goal of this paper is to basically think about the design of optimal screening contracts or mechanism in a single principal, single agent model when there are two basic assumptions are satisfied. These are situations where the principal cannot endogenously design transfer payments. So either the case of charity where the transfer payments, well, to think about transfer payments is, I mean, they don't even exist, right? That's a immoral thing to do, I guess, to pay the volunteers, or situations where the transfer payments are exogenously fixed because of some regulation, like in the context of the monopoly, right? So so that's the class of environments that I'm focusing on. And since the transfer payments are not allowed, the principal will be left with a single instrument, which is the agent's actions, in order to, if the principal wants, in order to screen the types of the agent, right? And the second thing is important is about the environment is that agents' preferences are single peaked. Now over a unidimensional or single dimensional action space. So that's a restriction. I'm going to focus on a single dimensional action spaces. And given the type of the agent, I'm going to assume that the agent's preferences over that action space are given by this inverted U-shaped function. And again, if it were not an inverted U-shaped function, if the agent's utilities, if all types of the agents had, let's say, strictly increasing utilities over the space of the actions, then you really cannot screen different types, right? I mean, if you have two types are not going to choose two different actions because their utilities are going to be, let's say, strictly increasing over the space of actions. So if one type prefers A to A prime, where A is greater than A prime, then the other type also prefers A to A prime. So all of them will actually pool to a single action. So if you really want an interesting problem, you need to have the assumption that the agent's preferences are single peaked over the space of the actions. Okay, so
Professor,
that's, yeah.
Can I ask? So
yes.
If the main objective is to screen, then a principal can simply offer their peaks, in the sense that just allow them and they can all choose the peaks, and
right.
that will
So
screen every.
Remember, but yes, that is one possibility, right? That you can just simply say, you know what, everybody choose whatever they feel like, right?
Right.
When everybody chooses whatever they feel like, they will obviously choose their
Choose
peaks,
their peak.
right? So that
Yes.
is a specific class of incentive feasible mechanisms. That's not the whole class of incentive feasible
Yeah.
mechanisms, right? Right.
True.
So
That
you
may
could,
not
yeah,
maximize
exactly.
the objective
Absolutely.
of the. Okay.
Absolutely, Sharvesh. That's precisely the point here. That yes, you could let them That's exactly what happens in volunteering, right? The charity lets them choose whatever they want, whatever effort they want to exert. But that's not necessarily. At least I'm arguing that might not be optimal from the point of view of the charity. So they might want to think about this more carefully.
Thank you.
So yeah. Okay. All right. So before I present you the formal model and the main results, I mean, I think it is important to get this out of the way. I mean, this paper, actually, I was not aware of the delegation. There is a literature on delegation. I was really not aware of this when I started doing all of this, but somebody pointed out to me. And fortunately, I did not replicate the delegation literature and wasted whatever years I spent on working on this. But there is a literature on delegation, starting with seminal paper by Holmstrom. These models consider a very similar environment where they consider a principal and agent model when the agent's preferences are single peaked over the space of typically a one-dimensional action space, and transfer payments are infeasible. So some recent work, actually Naveen Karthik et al., they have a recent work which came out also in June 2020 on this, but there is some history of work on this model. So I think it's important for me. I mean, this looks like exactly the kind of situation I'm considering, but there are some important differences. So let me just highlight those differences. So the key differences between delegation and what I'm talking about is that typically delegation models assume that the principal's preferences are also single peaked over the space of the actions. Okay, so principal has some ideal point and which might differ from the ideal point of the agents, and the principal is interested in making sure that, well, agents, when he delegates a set of actions to the agents try and choose something which comes close enough to his ideal point, right? But in my case, I'm not going to assume anything more than continuity of the principal's utility function. Okay, so it could take any shape, single peaked or not. All I want is a continuous utility function from the side of the principal. Okay.
Would you have some constraints besides the IC and IR constraint, like I want a total effort of this thing at least, or something like that, or you won't?
No, so no, I'm not. I'm just going to have IC and IR constraints. Okay. So in principle, you could allow for those kind of constraints on the principle that I want at the minimum, I want this kind of effort. I presume that that will one will have to think how that changes the characterization of IC and IR. I'm not sure at this point. I'm not sure. I can, because if your constraint is that I want, let's say, the expected effort, right, to be at least a certain amount, I think that. I mean, okay, so there are two ways to do it. Okay, a simple answer to perhaps would be that let me just solve the unconstrained problem using the techniques I'll offer, okay? And of course, if the unconstrained problem, the solution, let's say expected effort happens to be more than the minimum expected effort, then I'm good, right? Then I have I can ignore that constraint. But if it happens that I cannot reach that maximum expected that constraint, I can't hit that constraint, then within the class of mechanisms that then of course then I don't, I mean, then I can't solve the problem, right? Okay. Then I can't solve the problem. I'm overthinking that. Yes. So yeah, in principle, you could allow for such constraints and just use the unconstrained optimization to figure out whether such constraints are satisfied or are even feasible or infeasible, right? Okay. Next, the delegation models typically do not impose participation constraints on the agent, right? They basically, idea is that the principal is going to delegate a set of actions and the agent must choose amongst those delegated set of actions. The agent cannot say, I don't want to do it, right? Whereas in my case, I'm imposing participation constraints. The agent must the principal must ensure that if if he wants the agent to choose one of the quote unquote delegated actions, then the utility of that action is at least as high as the utility of the outside option. So the agent can always refuse to participate in the mechanism if none of the actions, delegated actions, are offer at least as much utility as the outside option. So I'm going to impose participation constraints. Although again, I mean, in the paper, I offer a generalization how if you were to remove the participation constraint, how the results are going to change. And it's not very drastically different, at least in terms of the general feel or qualitative feel of the results. Finally, and most importantly, I mean, I think there are some papers in the delegation literature which also don't, like I think Karthik's paper, Karthik et al., they impose IR constraints. So there are some papers which do that. So I think the most important key difference, I think, between my work and the delegation literature is that the delegation literature, as far as I know, in these papers, they focus on what is called on conditions under which interval delegation is optimal. Now, what do I mean by that? Basically, conditions under which the principal finds it optimal to offer a single interval of actions as the delegation set to the agent. Okay. So they try and find sufficient conditions for such a delegation set to be optimal. In my case, I don't presume any particular kind of restriction on the delegation set or the contracts. I'm basically more interested in offering a general technique, which is what I'll call the duality theorem, for solving any screening and delegation problem when transfers are infeasible. So there will be situations where applying this duality theorem, I'll find contracts which are not necessarily a single interval. The contracts could be disconnected intervals. Okay, so I believe that the results I'm going to offer are can be used to consider situations which are much broader than what have been typically typically looked at in the delegation literature. Examples of that being when let's say the density function of the agent's distribution of types is not unimodal. Okay, so what if it's bimodal? What happens then? So these are things that are not looked at in the delegation model, in the delegation literature, at least as far as I know. So okay, so yeah.
So it seems like the IC constraints and the IR constraints look the same in your model and the delegation model.
Yeah, if you were to impose the delegation, so for instance, if you were to assume that the utility function of the principal is also single peaked, and there are IR constraints,
but that will be in the objective function, I think, right? Principal.
Yeah, so that yes, the objective of the principal. Yes, so suppose the
IR constraints would be the same, I guess, for the.
Yes, they would be the same. Yes, if you were to impose the IR constraints, it would be exactly they would be the same. Yes.
Thanks.
So like if you look at Karthik et al., I think they are ones which do impose the IR constraints, and over there, they have a outside option, and as like them, I will also assume that the outside option is this zero action. Okay, so if you don't take zero action, then it's like that's the outside option. I think they impose exactly the same. So it will look exactly the same. So in fact, the two problems will be exactly the same if you impose IR constraints and you assume that the principal objective is single peaked. So they'll be exactly the same problems. That's why I said that I think the more important contribution, at least as far as I can see the difference, is over here in this duality theorem.
Sure. Thanks.
Okay. All right. So here is the model. Let's jump into that. So I'm going to outline the model. I'm going to characterize incentive feasible mechanisms. By incentive feasible, I mean IC and IR mechanisms. Then I'm going to provide you a duality theorem, which is basically going to tell you that the problem of designing optimal incentive feasible mechanisms is equivalent to a discrete time finite horizon dynamic optimization problem. Okay, and I think this duality theorem is useful because first of all, because using this duality theorem, I can show that the solution to the principal's problem exists. I mean, if you go back to the delegation literature, Holmstrom had some existence result, but he needed to assume lots of assumption things on the agent's utility function for him to get that result. As you will see, I mean, in my case, I don't necessarily need to make a lot of those assumptions like concavity and things like that of the utility function. So you can use the duality theorem to first of all argue for existence of the solution, and then you can apply that to solve general screening or delegation problems. And I think it's much easier problem to solve. Of course, sometimes you'll have to use things like dynamic programming or other numerical techniques, but those are things which, I mean, there's a vast literature on all of that. So I think this equivalence helps from that perspective. And then I'll provide you some nice pretty pictures to show you what are the different possible mechanisms that can be optimal for the charity. Okay. So let's jump into the model. So there is, again, this is sort of a repeat. There is a single principal and a single agent. Now the principal's payoff or utility is given by this pi function, which is a function of the agent's action. The set of possible actions could be any non-negative action, and the agent's type. The set of possible types could be anything greater than or equal to 0. Of course, I'm going to make an assumption about the actual distribution of types, which will restrict the support to be a subset of the real line. But for now, let's allow for all possible types, all possible actions. A equals to 0 will be the outside option. And whenever the agent of any type chooses the outside option, the principal's payoff is going to be equal to 0. So that's the principle. And here is the assumption for the agent. The agent's utility function is also assumed to be continuous, but it satisfies some other 4 assumptions. So a little bit more structure over here. One is single peakedness in the space of actions. U is single peaked at over the space of actions, and the ideal point, ideal action of any type theta is a star theta. Okay, so you will see this a star function floating around quite often in the next set of slides. So just keep this in mind. A star theta is the ideal or the optimal action of type theta. Okay, so that's the point of the peak over the space of actions. Next, willing actions are bounded above. What that means is that basically there is a high enough action which is such that which is worse than the outside option. Okay, so you can push the agent to take higher actions, but at some point the agent will refuse and say, no, I would rather choose the outside option than such a high action. Okay, so if you think about the inverted U shape, at some point it goes the U goes, if the utility at the outside option is equal to 0 for the agent, then at some point the inverted U shape cuts the x-axis, right, far enough to the right. I'm going to assume that marginal returns, that is the marginal returns with respect to the action for any type, this partial derivative over here, that it exists and is continuous in a function. Continuous in actions. Okay, so this partial derivative exists and is continuous in the actions, and that's the final assumption. The partial derivative, the marginal returns, are strictly increasing in type theta. So this is Arnava, this is in response to your question. I was mentioning that I'm going to make some assumption that relates the utility function of different types. So that's the assumption I have, strictly increasing marginal returns. So the marginal return of any of the action is, if I fix the action, then it is strictly increasing in the agent's type. Now this assumption, I don't know, I mean, whether this is the most popular assumption out there in the screening literature, but this is weaker than assuming this Spence-Merle's single crossing condition, right? Which that Spence-Merle's condition requires actually the cross partial. It's a condition on the cross partial, so it requires that the function will be differentiable in both theta as well as in A. I'm not assuming any of that. I just require differentiability with respect to the action and continuity of that derivative in these in action, and strictly increasing in the type. In fact, I could drop these last 2 assumptions. I don't even need to have a differentiable utility function as long as 2 other assumptions are satisfied. So the whole point of imposing strictly increasing marginal returns are actually these 2 things I get out of it. Strictly increasing marginal returns implies strictly increasing differences. Now that's something which is pretty standard also in the literature, which basically says that if you take any 2 types, theta greater than theta prime, then the utility difference for these types is strictly increasing in the action space, okay, in the agent's action. So this difference U of A theta minus U of A theta prime is strictly increasing in A. So that is strictly increasing differences, and that's an implication of strictly increasing marginal returns. The second implication of strictly increasing marginal returns is that this function A star theta, which is the function of optimal actions, is also strictly increasing in theta, okay, in the agent's type. So higher types, the ideal actions of higher types are higher. And this is a result by Edlin and Shannon in 1998. So as I said, we can drop the assumption on marginal returns. So I don't even need to have differentiability of the utility function as long as these last 2 assumptions, are true, okay? In fact, for all the proofs, I basically use these 2. I don't even talk about the derivative of the utility function. So you can just work with continuous utility functions that are single peaked and satisfying these 2 assumptions, okay? And again, an important difference again with respect to delegation literature, although they also assume single peaked over the space of actions. Typically, the assumptions about single peaked over the space of actions, in addition to that, they also assume concavity. Notice I'm not assuming anything about the concavity of the utility function over the space of actions. I mean, it doesn't have to be a nice U shape. It could be like, I don't know, upside down tumbler or something, right? Which is not necessarily concave. Okay, so that's the basic model. Another piece of terminology that might be helpful is the maximum action that an agent of type theta is going to be willing to take. So that's going to be noted as a bar of theta. So given that we have a single peak utility function over the space of actions, this is the action which is such that type theta is indifferent between the outside option and that action. Okay. So that's how you find this a bar of theta. And a result which is noted in the paper is that a bar of theta is obviously greater than the ideal action of type theta. And also this function, when I view it as a function of theta, a bar theta is strictly increasing in theta and continuous actually also in theta. Okay. So so both a star and a bar theta, these functions are strictly increasing and continuous in theta. With a bar theta being above a star theta all the time. Okay, the agent's type, as typically, is private information, and it is distributed as some G on some interval, theta lower bar to theta upper bar, with some density which is positive and continuous in the interior of the interval. So those are pretty standard assumptions. And what the principal does is the principal defines a contract, which is a menu of acceptable actions. So some subset of the real line, because real line was a set of all possible actions. So the principal defines, this is like the delegations, right? So it says, okay, you can only choose, if you want to participate in the mechanism, you can only choose actions within this set A. Well, the agent obviously has the outside option always available to him. So the agent of type theta is going to choose either an acceptable action in A or the outside option. And the choice will be the one which maximizes the agent's utility. All right. So that's why we are going to be imposing participation constraint, because the agent always has the outside option available to him. If I remove this, then we are back in the delegation literature where the agent only chooses an action in A in the delegation set. Okay. Okay, so quick definition. I mean, all of you must be familiar, but okay, a mechanism is now going to be a function which is going to specify an action for each type of the agent within the support of the distribution of types, right, within this interval. It's going to be incentive compatible if for every type choosing its own action, mu of theta, is going to be at least as good as trying to mimic another type. So by which I mean trying to choose an action for another type theta prime in the mechanism. Okay, so incentive compatibility is pretty standard over here. Then we have individual rationality, which says that the agent wants to participate in the mechanism, which means that by choosing the action prescribed in the mechanism, the agent gets at least as high payoff as by choosing the outside option, right? So these are standard IC and IR constraints. Now, what's the relationship between the space of contracts and the space of mechanisms? Well, we have the standard revelation and taxation principles that also applies in this scenario. So every contract is going to be equivalent to an incentive compatible and individually rational mechanism with at most countably many points of discontinuity. So that's important over here because, and I want to emphasize this phrase over here, with at most countably many points of discontinuity, because what I'm going to do later on will be slightly restrictive. So every contract is going to be equivalent to an IC and IR mechanism with at most countably many points of discontinuity, and vice versa. So if you give me an IC and IR mechanism with at most countably many points of discontinuity, I can create a contract, which, remember, again, is a subset of the real line, or the positive part of the real line, which is equivalent to this IC and IR mechanism. In the sense, equivalence in the sense of what? In the sense of the principal's expected payoff, as well as in terms of outcomes for almost all types. So this equivalence is pretty strong. It's not just in terms of the expected payoff of the principal, but also in terms of the outcomes. Okay, so because of this result, I mean, we can just focus on, instead of focusing on the space of contracts, I mean, which is much more complicated to work with, we can focus on IC and IR mechanisms with at most finite points, countably many points of discontinuity. Okay, so here is the characterization, and you will immediately see the restriction I'm imposing. So I'm going to be looking at mechanisms which have at most finite points of discontinuities. Okay, so give me any mechanism with at most finite points of discontinuity. So within that class of mechanisms, what does an IC and IR mechanism look like? Well, here is the theorem. This is the characterization of such IC and IR mechanisms. The mechanism mu is going to satisfy these two constraints if and only if it is going to be increasing and piecewise function. So by increasing, I always mean weakly increasing. If I want to say strictly increasing, I will say strictly increasing. Okay. So if and only if it is increasing and a piecewise function. So just imagine an increasing and a piecewise function where each piece is going to be either constant, okay, it's going to be flat, or it's going to coincide with the A star curve, okay, A star function. So each piece is either flat, constant, or it's going to coincide with the A star function. That's one. The second thing is, let me look at any point of discontinuity of this mechanism, right? Let's say theta k, right? That's the point of discontinuity. Then at that point, the discontinuity must be a jump discontinuity, okay, such that type theta k is indifferent between the left and the right side limits of the mechanism at point theta k, okay? So type theta k must be indifferent between, so when I look at the behavior of the mechanism and take the left and the right hand side limits at theta k, then the type theta k should be indifferent between those two limits. And the last restriction is basically coming from the participation constraint, that the action prescribed to each type must be between 0 and the maximum action this type is willing to undertake, okay? Because notice the individual's utility is single peaked over this interval, and beyond this interval, all actions are worse than the outside option, okay? So just these three conditions. Now, what I want to do, of course, I'm not going to be able to give you a proof, but briefly give you a sense of why these things are true. So why these things must be necessarily true for an IC and IR mechanism. So let's look at some pictures. But before I do that, what will, yes?
Ask a quick question.
Yes.
Can you go back to the characterization again? So
yes.
So it looks like, it's a little messy characterization, because there are these discontinuities of this mu function.
Yeah.
I was wondering if you, instead of using mu, if you were to characterize it in terms of u, so u of mu theta, how it behaves,
right.
Would that be a cleaner characterization? Because usually what happens is this mu can be discontinuous, as you were rightly showed,
right.
but the u is usually continuous in the interior and so on. So it's actually quite well behaved. So I was wondering if you can get a better, neater characterization if you were to characterize it in terms of u function.
Yes, so indeed, yes, I think yes. The utility function will be, when I look at it, will be well behaved. It will be continuous. I don't know how that, because the duality theorem follows very closely this characterization. Okay, so this relationship between IC and IR mechanism and this dual problem. I mean, I got that relationship by precisely overlooking this beautiful properties of the utility function in an IC and IR mechanism. So I'm not sure what, if I were to give you a characterization in terms of the utility function, what that would mean for this duality theorem, if I can even provide a duality theorem of that type. And you will notice, I mean, the duality theorem is over the, like, it is going to be basically very closely following this characterization. I mean, so I'm not sure. So yes, it could be cleaner, but I'm not sure whether it helps me in the second result.
Okay.
And in fact, I mean, that was precisely what I did. I did when I noticed that there are these discontinuities, and I saw, okay, earlier literature usually focuses on, they discard these discontinuities and focuses on the utility function because that is well behaved. But I started thinking more about these discontinuities, and that led me to this duality theorem. So I'm not sure whether that would be eventually be useful or not. I don't know.
Sure.
But Rene, I mean, just if you look at the theorem here,
Yeah.
I mean, 2 is essentially saying that you know, both 1 and 2 are actually saying that, you know, there are no utility jumps, right? That's
Yes, exactly.
So
Exactly.
if you, you know, proving that, I mean, you could, if you prove this, then proving that it's well behaved in utility space is not, should be.
Yeah, that is pretty straightforward. Yes, I completely agree with you. What I'm saying is, while that might be true, I don't know what that means for this this duality result, which is going to be that, hey, the class of ICNIR optimal ICNIR mechanisms is equivalent to this class of dynamic optimization problems.
Okay,
So I don't I don't know. I mean, whether that relationship will hold and what that will look like, I don't know. So that's why I can't answer that question, but I do agree. Yeah, 1 and 2 automatically imply that the utility function is well behaved. That's true. Okay, so let's just quickly recall this fact, which I mean, it's well known, right? IC basically implies monotonicity, right? So in my case, because of that strictly increasing marginal returns, monotonicity means that the function must be increasing. Okay, so if the mechanism satisfies incentive compatibility, then it must be increasing. So let me not go into a proof of that. That's a pretty standard result in mechanism design. So, but let's use that result to try and understand these flats. Okay, these flat portions and these portions which coincide, these pieces of the ICNIR mechanism. So let's say a type theta 1 is prescribed an action which is greater than her optimal action in the mechanism, right? Mu of theta 1 is greater than A star theta 1. Now, my claim is that if you consider these types in the interval theta 1 to theta prime, then all these types, the mechanism over this interval must be constant. That is, it must look like this. Now, what is the reason behind that? So to understand the reason behind that, let's see if I can use this over here. Allow me to use that. Okay, so let's think about a point over here. Okay, this point over here. Let's look at this type theta. Since the mechanism must be increasing, either the mu of theta must be equal to this mu of theta 1, or it can be greater. It cannot be below that, right? So my contention is that in this interval, mu of theta cannot be greater than mu of theta 1. And the reason for that is single peakedness. Because if this was mu of theta, oh wow, this is not looking very nice. Sorry. So if this point was mu of theta, right, over here, if this point was mu of theta, then since the utility function is single peaked, type theta would strictly prefer mu of theta 1 to mu of theta. Why is that? Because remember, there is a U-shaped utility function. The type theta's optimal action is below mu of theta 1. So as we go further away from that optimal action of type theta, then his utility is going to be falling. That means that mu of theta 1 is strictly preferred to mu of theta. So we will fail incentive compatibility if in this region, the mechanism was strictly increasing. So it must have a flat in this region, okay? Similar argument on the other side. If a type theta 1 is prescribed action which is below its optimal action in the mechanism, then in this range of types, the mechanism must prescribe again a constant action which is equal to mu of theta 1. So that explains the flat part, right? I said each piece must be either constant or coincide with the A star curve. So let's come to the coinciding with the A star curve. So let's look at a type theta. We looked at a type theta 1 who was either prescribed a higher or lower action than its optimal action. So now let's look at a type theta 1 who's prescribed her optimal action by the mechanism. So mu of theta 1 is exactly equal to A star of theta 1. In that case, my first argument is that the mechanism must be continuous at point theta 1. Okay, so that's my first claim. Suppose not. Suppose the mechanism is not continuous at theta 1. Let's just say, for the sake of argument, that the right side limit of the mechanism is above mu of theta 1. Okay, that is what it would mean to be discontinuous. Now, similar argument as in the previous 2 slides about the flat portions of the mechanism will imply that to the right, up until I intersect the A star curve, the mechanism must be a flat. It must be constant at this right-hand side limit, okay? Now, what does that mean? That means that these types which are close enough to theta1, some folks over here, these types would strictly prefer mu of theta1 to this constant action, which is greater than mu of theta1. Why? Because their optimal actions are much closer to mu of theta1 than this constant action. And remember, utility function is continuous for the types. So these folks near theta1 but slightly to the right of theta1 will always prefer mu of theta1 to this constant action, and that again violates incentive compatibility. So in fact, since I've assumed that the mechanism must have at most finite points of discontinuities, not only should the mechanism be continuous at theta1, it must be continuous in a neighborhood around theta1. So you can argue that because I'm assuming only finite number of points of discontinuities. So there must be an open interval around theta1 such that the mechanism is actually continuous. What does that mean? That basically leaves us, when I combine it with the argument for the flat portions of the mechanism, that leaves us with basically 4 types of possibilities in the neighborhood of theta1. One possibility is that the mechanism is completely flat, is constant in the neighborhood around theta1. The other possibility is, well, it is initially constant and then coincides with the A star curve in the neighborhood of theta1. Third possibility is it's initially coincides with the A star curve in the neighborhood and then is flat. And the fourth possibility is that it is coincides with the whole A star curve in the neighborhood of theta1. Okay, but in any case, moment the mechanism intersects the A star curve, it must be continuous around the neighborhood. So there must be a portion around there which will coincide with the A star curve. It cannot jump away from the A star curve in the neighborhood of theta1. Okay, at least in one direction. You can have, or it can be completely flat. So, okay, so that hopefully gives you at least some intuitive flavor of why it must be a piecewise function, which is increasing and where each piece is either constant or coincides with the A star curve, okay? The final point about jump discontinuities, that's, again, I believe most of you would already have the intuition for that, but let's look at this situation where type theta1 so let's look at a situation where the mechanism is discontinuous. As already argued, discontinuity can only happen when theta1 is prescribed an action which is different from A star of theta1. So let's say theta1 is prescribed an action mu of theta1. Then since the mechanism is discontinuous, so first of all, since mu of theta1 is greater than A star of theta1, the previous argument means that on the right hand side, the mechanism is constant until it hits the A star curve. What about on the left hand side of theta1? What does the mechanism look on the left hand side of theta1? Well, theta1 must be indifferent between mu of theta1 and whatever is the left hand side limit of the mechanism at theta1. And that's because if that is not true, if theta1 were not indifferent between the right hand and the left hand side limits, then either theta1 or somebody near theta1 would want to deviate. Okay, so since theta1 must be indifferent between the left and the right hand side limit, now where is that indifference point for theta1? Again, we have single peak preferences, so that indifference point must be below the A star of theta1 point. Okay, so it must be below this curve over here somewhere. Because again, remember, recall the U-shaped curve of type theta1 over the action space. And now again, using similar arguments about the flat portions of the mechanism, you can argue to the left of theta1, the mechanism must be flat at this left side limit, which is indifferent to the right side limit. Okay, so that's how the mechanism will look on the left and right hand sides. So hopefully this gives you some intuitive flavor of why that characterization result is true. I must point out, in one of the delegation papers, I think it's, maybe I'll butcher his name, Melmuland and Sibano, if I'm not mistaken, they do provide necessary conditions on IC mechanisms in delegation literature, which look similar, but to provide those conditions, they impose additional restrictions on the utility function, like concavity and stuff. Here, I'm not doing that. I have much weaker conditions, but more importantly, I'm providing a full characterization. Okay. Okay, so hopefully you have some intuitive flavor of the characterization result. And let me just briefly talk about how large this class of mechanisms is. I mean, while I'm focusing on restricting to mechanisms with finite points of discontinuity. This class of mechanisms includes things like agent optimal mechanisms, right? Which are the mechanisms, I think one of you asked, where you let the agents just choose whatever is optimal for them. That's one possibility. Indeed, that such a mechanism is going to be IC and IR. But you can have other possibilities like a take it or leave it mechanism, where basically the contract is a single point. You either accept that action or you don't accept that action. So types who are willing to accept that action choose that action. These are these fellows between theta1 and theta bar, upper bar. And the types who are not willing to choose that action, these are types between theta upper bar and theta1. They choose the outside option. So that's a take it or leave it mechanism. You could also have a minimum acceptable action mechanism. So in that mechanism, the principal basically offers a contract in which he sets a minimum level of minimum action that you must undertake. If you choose to take higher action, that's fine, but you must at least take that, minimum action. Okay. So so here A tilde is that minimum action. Some types are not willing to even take that minimum action, so they are excluded by the mechanism. Some types are willing to take that minimum action but no higher, and then there are types over here who are willing to take a higher action. Since that could be anything, they go ahead and choose their optimal higher action, right? Because the only restriction is the minimum should be A tilde. It can be anything else above that. Another possibility is tiered mechanisms. These are mechanisms. So here I have an example of a two-tier mechanism where the principal basically sets the contract is either you take the low action or the high action, and this is the low action A1 and the high action is A2. So those types, again, sort themselves out. I mean, the types who don't want to take either of the actions choose the outside option. These types within the range theta1 and theta2 choose the intermediate action. The low action, and the types above that choose the high action, and so on and so forth, right? I mean, the class of mechanisms can be fairly complicated. You can have all sorts of jumps. Notice I'm allowing for any number of finite number of jumps, so all sorts of jumps, then coinciding with the A star curve, then jump, then another jump, then coinciding with the A star curve. So it can be a complicated mess in terms of the class of mechanisms. But having said that, I mean, still, it's a restriction. I mean, because remember the taxation and revelation principle said that the space of contracts is equivalent to the space of IC and IR mechanisms with at most countably many points of discontinuity, whereas I'm restricting to things with at most finite number of points of discontinuities. Yeah, so that's a restriction of there is a limitation to the characterization, but I would want to argue that actually that limitation might not be so relevant from a practical point of view, because I mean, offering a mechanism with countably many points of discontinuity, or even actually many points of discontinuity, is pretty strange, because anytime you add a discontinuity point, what is your contract going to look like? It's going to look like a set of disconnected intervals, right? So for instance, over here, the contract will specify this action, the low action, then all actions between this point and this other point over here, this interval of actions, and another third point where this action, right? So the space of contracts, as you keep adding more and more points of discontinuity, is going to be very fine, like a large number of disconnected intervals. Which seems pretty strange from a practical point of view. Okay, so in fact, for the optimality result, I'm going to focus on actually problems where the principal says, okay, I'm going to be willing to accept at most k points of discontinuity, where k can be any large number you feel like, but there is an upper bound on the number of points of discontinuity. Okay,
Professor,
so
can
when
I ask one thing?
Yes, please.
Can you just please go back in the previous figure?
Yeah.
I have seen that in all of these figures, whenever you have a discontinuity, the point is included in one of the limits, either it's in
Yes.
the left or right. So why can't
Yeah.
the like contract can have a like even the both points? So it seems that in the at point theta 2,
Hmm.
the this the dotted point is the closed one, but the
Yes.
interval above that is the starting open one, right?
Yeah. So this interval over here is excluded from the contract. So in the
Why?
mechanism, notice if I were to include this in the contract, if I allow individuals to choose a point in this interval, right, between this empty dot and the fill dot, then type theta 2 will actually choose a star theta 2. Okay.
No, Professor, I meant to ask that suppose the blue dot point is some say action 5, and the empty circle is action 10.
Mm-hmm. Okay. So
Then
this is 5, that is 10. Okay.
yes, yes. So so your contract is saying that the at the closed interval at 5,
Mm-hmm.
including 5, but
Yeah.
the next interval is the open interval from 10, right?
Well, it's not really open. It's just the point 10. It's actually a closed point. It's a
Oh yes, yes,
so
yes, yes.
it's a 10. It's
It's a
only point 10.
constant
Okay.
action. Yeah, yeah, sorry.
It's a constant
Okay.
action. So yeah. So what is true is in the mechanism, when I look at the space of mechanisms, I am free to choose this point, whether the theta 2 should be
5 or 10, yes,
prescribed this
yes,
5 or 10. Because he is indifferent. Okay.
yes.
So there is an equivalent class of mechanisms in that sense. But in the space of contracts, it doesn't matter. Both these
It
actions will show up.
doesn't matter. Absolutely right.
Yeah, it doesn't
Okay.
matter.
Thank you,
Okay.
Professor.
So Rene, just
Yeah.
keeping tab on time, you have about
Yes.
15 minutes, I think.
Okay. Yes, sure. So I'm going to go to my duality result now. Okay. So, but I do want to clarify in some sense, the constraints I'm imposing. I'm saying that the principle is comfortable with only up to a finite number of points of discontinuities, where that finite point, where that upper bound is some k. Okay. I'm not going to fix the k. I'm sorry. I'm not going to prescribe a specific value of k, but k can be anything. But the principle says, well, let's say I only want to have 10 points of discontinuity in the mechanism. And again, the reason why am I doing that is because anytime I introduce a point of discontinuity, I need to basically remove a portion of the action space that can be allowed. So I need to have a finer and finer contract, and such a fine contract perhaps might not be feasible in that sense. Okay. Okay, so this is the principle's K primal problem. That's what I'm going to call it. Basically, choose a mechanism, mu, which maximize the principle's expected payoff, subject to the fact that mu satisfies IC and IR, and has at most K points of discontinuity. Okay, so that's a important thing. It has at most K points of discontinuity. And now my claim is that this K primal problem, right, where I fix the K, the upper bound on the points of discontinuity, that K primal problem is going to be equal to this dual problem, which is a dynamic optimization problem. Okay. So what is this dual problem? This dual problem has basically, think of a problem with 2K plus 3 periods. So if let's say K is the upper bound on points of discontinuity is 2, then this is a problem with 5 periods. Okay. If the upper bound on points of discontinuity is 3, then this is a problem with 9 periods. Okay. So this is the number of periods in the problem, which depends upon the upper bound on the points of discontinuity, 2K plus 3. Now, what does the decision maker do in this dynamic problem? The decision maker's problem is to actually find a path. It's find a path from 0, the initial action or the initial state in period 0, to this action in the terminal period. What is this action? Notice this is the highest maximum action that the highest type in the support of the distribution of types is willing to take, a bar of theta bar. So the decision maker's problem is to go from 0 to this high action, okay, in these 2K plus 3 periods. In each period, the decision maker is going to choose the next period state or action. So in period n, he chooses an plus 1. With two restrictions, the next period's action, an plus 1, yeah, must be at least as high as an, okay, And you can already see why this should be true. Remember, we have the mechanism should be weakly increasing. So that's where this is coming from. And secondly, the first period choice, the choice in period 0, the first action chosen in period 0, A1, that should be no more than the maximum action that the lowest type is willing to undertake, okay? A bar of theta lower bar, okay? So that's the dynamic optimization problem. It's a simple finite horizon dynamic optimization problem, where you are moving from an initial state, a given initial state, to a given terminal state in those finite number of periods, with the restriction that this the choices should be weakly increasing, and this is the restriction on the initial choice, okay? What are the, obviously I need to specify the rewards of the decision maker. The rewards of the decision maker depends upon the period. So literally just think about the following. So if the period is odd, then in that period, the decision maker is allowed to quote unquote slide, okay, smoothly slide to the next action, okay? And I'll specify what I mean by this slide in a bit, but the decision maker is allowed to smoothly slide from the action, current period's action AN to the next period's choice, AN plus 1. And in that case, he gets a payoff of pi 1, all right? In other periods, any period which where n is not odd, then the decision maker is allowed to jump from the current period's action to the next period's action, and that jump gives him a payoff of pi 0, okay? So what are these slides and jumps? Well, these slides and jumps coincide with when the mechanism is continuous between AN and AN plus 1, and when the mechanism is discontinuous and there is a jump between AN and AN plus 1. So let me show you the pictures. So if the mechanism were continuous between AN and AN plus 1, then the principal's expected payoff over the corresponding interval, where theta star AN is the inverse of A star, right? The theta star function is the inverse of A star function. So when the mechanism is continuous over this between AN and AN plus 1, then the reward of the principal, or the principal's expected payoff in the corresponding interval, is basically pi 1, okay? So here the decision maker in my dynamic problem is going to be moving smoothly or sliding smoothly between AN and AN plus 1. So that's why I'm calling it a slide, all right? What about a jump? Now, suppose the mechanism has a jump between AN and AN plus 1. That means that a single jump between AN and AN plus 1. In that case, the principal's expected payoff in this over this interval between theta star AN and theta star AN plus 1 is given by this pi 0 function, okay? In this portion, up until the point of up until the type who's indifferent between these two actions, the principal's payoff is given by the fixed action AN, right? And the corresponding types in those intervals. And in the following interval, in the next interval, the principal's payoff is given by the fixed action AN plus 1 and the type theta, okay? So whenever the thing jumps, then this is going to be the principal's payoff in the corresponding mechanism, okay? And that's what pi 0 function is for our decision maker, okay? So my claim is that this is the K dual problem, is to find such an increasing path from A0 equal to 0 to some A bar of theta upper bar with this additional restriction. And in that dual problem, the principal's expected, the decision maker's payoff will be given by these pi 0 and pi 1 functions, starting with pi 0. So because period 0 is not odd, so over there your payoff will be, you are required to jump from one action to the next. In period 1, you are allowed to slide from one action to the next. Then you are allowed to again jump, then slide, jump and slide, and so on and so forth, okay? So that's going to be the K dual problem. And my claim is that these two problems are going to be equivalent, okay? So let me just briefly show you why this equivalence holds. I mean, it's actually, once you look carefully at the mechanism, it perhaps is not too difficult maybe to come up with this duality theorem. But let's suppose this is my mechanism, okay? This is my ICN IR mechanism. And now what I want to do is for you construct a path which goes from A0 equals to 0 to A bar of theta bar, upper bar, okay? I want to construct such a path which is a series of jumps and slides so that the expected payoff in this mechanism is equal to the decisions makers expected payoff in the dynamic problem.
So will you
So how do I do that?
Will you
Yeah.
explain how 2k plus 3 periods are coming?
Yeah, that basically that's sort of it's literally like an accounting identity. So I'll explain to you over here. So now
Okay.
notice over here there is one jump right now. Okay, there is one jump in the mechanism. So this is a mechanism with one jump, or it is within the class of mechanisms with two, at most two, or at most three, or any number of at most any number n greater than equal to one jumps, right? So basically that 2k plus 3 is coming from the fact that the way I'm measuring the payoffs in each period, right? So let's just try and see if I can explain that intuition using this picture. So first thing what I do is I increase the size, I extend the mechanism to a larger type space. Okay, what is this larger type space? So I move from type space theta lower bar to theta upper bar to a type space going from 0 to this particular type. Who's this type? This is the type who finds it optimal to play this maximum action in the state space of the dynamic problem. Okay, so first of all, I extend this mechanism in an incentive compatible way to this larger type space. And the way I do that is basically just, as you can see, I have a flat all the way and then another jump. The point of jump is this type is indifferent between these 2 points. Similarly over here, type theta lower bar is indifferent between these 2 points. Okay. Next comes, okay, so now first of all, I extend this mechanism. Notice this mechanism, the expected payoff on this extended mechanism is exactly the same as the expected payoff on the original original mechanism, right? Because, well, by the fact that the density is only the distribution is only supported on this theta lower bar, theta upper bar interval, all these fellows over here, all these other types, they have zero density. So, I mean, they are irrelevant from the perspective of expected payoff. So this extension does not affect the expected payoff of the principal. And then comes these jumps and slides, okay? So notice in the first period, so where are these actions that I'm going to be jumping and sliding to? These are the actions that which are given by these intersection points. Notice intersection points between what? Intersection points between this extended mechanism and the A star curve, okay? So this is the first intersection point, A0. Okay, so this is my state space. The first intersection point is A0 over here. The next intersection point is going to be this one, A1. Third one, or whatever, third intersection point is going to be A2 over here. Then I have an intersection point here, A3. But now, if you look at this problem over here, what I have is, since I wanted to have 2k plus 3, right? So, and there was only one point of discontinuity, I need to have 5 points in my dynamic problem, 5 periods in my dynamic problem. So the A3 and A4 are going to be exactly the same. And then finally, I have A5, all right? So now where are the jumps in the slides? Well, you have a jump first, then you have a slide. It's a smooth path. Then again, you have a jump, right? Now, where is the slide between A3 and A4? Well, it's the same point. So you can call it a jump or a slide. It doesn't matter. The payoff of pi 1 and pi 0 is exactly the same. So let's call it a slide. And then finally, you have a jump again. Okay. Now, I'm still trying to think about if there is an easy way for me to answer Debashish your question, why 2k plus 3? I mean, I think the idea is basically what I wanted was an equivalence in the payoffs of the two problems, right? I wanted these to be completely equivalent in terms of payoffs, and I believe there might be other ways to rewrite these payoffs where you need not have so many periods, but if you want them to have this equivalence, you need to the way I'm measuring it, I'm allowing this nice structure where you alternate between jumps and slides, right? So with that structure, I need to have enough such points or periods in order to have the two things have the same expected payoff? I know it's not a very clear answer, but unfortunately, I don't think, I mean, perhaps I'll have to think a little bit more if I can give you a better intuition. But in some sense, it's a kind of an engineering kind of answer, that's what makes these problems equivalent.
That's fine.
Okay, so hopefully this helps you get a sense of how, from a given IC and IR mechanism, you can construct this increasing path from A0 to A bar of theta upper bar, where the path is this alternating jumps and slides, and the payoff along this path, you will notice, is exactly the same as the payoff in the expected in the IC and IR mechanism, right? Over this interval, when you have a jump, the principal's payoff in the mechanism is exactly equal to the pi 0 function that I have in the dynamic problem. Over here, there is a slide. So of course, the principal's payoff and the decision maker payoff over this interval is the same, and so on and so forth, okay? Hopefully, as I said, yeah, this gives you some sense of why one way is true, right? Why starting from an IC and IR mechanism, you can construct such a path in the dual problem with exactly the same expected payoff as the principal's expected payoff in the mechanism. But the reverse is also true, right? So if you give me such an increasing path, then I can construct an IC and IR mechanism which has exactly the same expected payoff for the principal as the total reward of the decision maker on this increasing path. So the duality theorem goes in both directions. So it's a strong duality in that sense. If a mechanism solves the K primal problem, then the corresponding sequence of actions that I just constructed solves the K dual problem. And similarly, if I have a sequence of actions that solves the K dual problem, then there is a corresponding mechanism that I can construct which solves the K primal problem. So in that sense, the K primal problem is equivalent to the K dual problem. And my claim is that that is a much easier problem to work with than the K primal problem. And the proof of that claim is that, well, first of all, it's much easier to argue that there exists a solution to the K dual problem, because you can easily show that it is basically what I have in the K dual problem. If you go back, it's oh, come on, go back. Yeah, here's the K dual problem. What I have is a continuous function. Notice pi 0 and pi 1 are continuous in the actions. It's a continuous function defined over a compact interval, which is a compact set, which is defined by these inequalities. So I do have a solution to the K dual problem, which means there is a solution to the K primal problem for any K. So no matter what upper bound the principal fixes on the maximum number of points of discontinuity, there is a mechanism which solves the principal's optimization problem. And secondly, this problem, this K dual problem, is a dynamic optimization problem. There are many techniques available to solve this. There are books written on this. Unfortunately, I'm not a specialist on that, but I know that things like dynamic programming, if you can't use some basic straightforward Euler equations kind of things, you can use dynamic programming. You can use numerical methods to solve this. So this sort of transformation helps you solve and tackle a much broader class of things than that has been done, for instance, in the delegation literature. Okay, and let me now, because I don't have much time, let me now show you some pretty pictures for, as I promised, for the charity example. So I'm going to go back to the charity example and show you the kind of mechanisms that can be optimal for the charity under the different circumstances. Remember, we have a single peak preferences for the individual or the volunteer, and in that case, you can show, for results like this. Suppose the marginal benefit of effort is strictly convex. In that case, and types are uniformly distributed on 0 to 1. Then in that case, the optimal mechanism for the charity is the agent optimal mechanism, where the charity lets the agent choose whatever amount of effort he wants to exert. So do not impose any restriction on the agent. But suppose the marginal benefit of effort is strictly concave now. That will have implications for these A star and A bar curves, and the types are still uniformly distributed. Now, in that case, the charity actually goes to the extreme opposite. The charity makes a take it or leave it offer, in the sense that a take it or leave it contract with a single action is optimal for the charity. So it fixes this action, and all types who prefer this action to the outside option choose that action. All other types choose the outside option. Let's look at the other case which is left out, where suppose that this marginal benefit of effort is linear. In that case, the A star and A bar curves are going to be linear. And in fact, I have a single peaked and symmetric preferences over here. So the slope of the A bar curve is going to be exactly twice as the slope of A star curve. In that case, you will have multiple solutions to the charities problem. So in fact, this agent optimal mechanism, which coincides with the A star curve, is optimal. Also, this mechanism where you have a take it or leave it mechanism, where the charity only accepts this action A tilde, which coincides with A star 1. That mechanism is also optimal. So the black line and the blue lines, those are two optimal mechanisms. And you can see why that is the case. I mean, here actually is a very straightforward intuition for why both these mechanisms must be optimal. Notice that the charity's expected payoff when I go from the black line to this blue curve is exactly going to be the same. Why? Because what the charity loses on this interval, which is given by the area of this triangle, this is the expected loss of the charity when it goes from the black line to the blue line. That triangle, the area of that triangle, is exactly equal to the area of this upper triangle, which is what it gains when these high types undertake the A tilde action. Okay, so when things are linear, you can have a very straightforward intuition why everything is why we have such multiple solutions. Things are slightly more challenging for the first two cases that I mentioned to you, and over there I do use my duality results to argue those cases. A few other 2 or 3 other pictures, and then I'll stop. So suppose, I don't know whether you can see it, suppose now let's go back to the case where the marginal benefit of effort is linear, but forget the uniform distribution of types. Let's look at this distribution of types. It's a unimodal distribution. In fact, it is a beta distribution with parameters 2, 2. It's a nice and symmetric distribution. This is the density function on the left-hand side. In that scenario, you can show that a minimum acceptable action mechanism is optimal for the charity. So it accepts any action above 0.375. And so all these fellows choose 0.375. Other fellows choose their optimal action. And these types, lower types, basically choose the outside option. I can also tackle, as I mentioned, bimodal distribution using this duality theorem. So if I look at the bimodal distribution, and v theta is linear, then in this case, let me look at mechanisms which are optimal within the class of mechanisms with at most 2 points of discontinuity. In that case, this mechanism happens to be optimal for the charity, which is a 2-tier mechanism. So the charity accepts a low effort or a high effort and nothing in between. So these fellows choose the low effort. The really low types choose the outside option, and the high types choose the high effort. So this is not always true for all bimodal distributions. Here is another bimodal distribution where things can look even very different. Notice over here, again, we have a bimodal distribution, but the charity does not exclude anybody. Now the optimal mechanism for the charity is like this. All these types between theta and 0.66 choose a level of effort between 0 and 0.1. And types between 0.66 and 1 choose the level of effort 0.56. So notice nobody is excluded in this mechanism compared to the previous cases. So hopefully that gives you an illustration of the usefulness of the duality theorem, how I've been able to apply it to these circumstances. Of course, you can apply it to other cases as well, and try and obtain whatever is optimal with the restriction that you want at most a finite number of points of discontinuity. Okay, so that's the conclusion. basically you can think about lots of extensions, I mean, multidimensional actions, multidimensional type spaces, allow for stochastic mechanisms, think about situations where there are multiple principles and a single agent with single peak preferences, or a single principle and multiple agents with single peak preferences. Again, situations where the key is that the designer is not, or the principal is not able to design arbitrary transfer payments. What is the implication of that in these scenarios? Those would be natural extensions to think about. And I don't know whether you will get some nice one can get clean results, as hopefully I have, but these are definitely things worth pursuing. So I should stop talking now, but thank you.
Okay, thank you very much. So we are over time, but if we have some time for questions. Please, if anyone wants to ask questions, go ahead.
So hi, Rene, just,
Yes.
you know, the last point in your conclusion, single principal and multiple agents with
Yeah.
single peak preferences. Actually, there is a nice model of this, you know, which is that Sprumont model. So
Whose
for
models?
instance,
Can you repeat?
Sprumont.
Sprumont. Okay, Sprumont. Okay.
Yeah. So this is the so it actually has an additional constraint. So suppose you want people to supply effort, but the sum of efforts has to be X. You know, you want to get, you know, so actually you get a very nice mechanism, which is this uniform rule, which is that you ration people on both sides. You know, you ration people on the same side. Sorry. So I mean, you look at the A star theta of both guys. If they just happen to be optimal, then wonderful.
Great. Yeah.
If not, then you. If they both exceed, then you have to ration them both less, and you do it by some sort of thing of a competitive, you know, which has equivalent of a competitive. I mean, there's an interpretation like that, you know, fixed price.
Right.
This thing.
Okay.
And the thing is actually, you know, you have a lot of handle doing that. And so what's the optimal mechanism there as well? I guess you have, you know, I'm not sure. I mean, is it unique? So I don't know, but it's a nice, you know, in some way you can think of, you're looking at the single version, single player version of that, and that's actually, you know, has many more contracts available, and so there's a serious optimization. But if you have two and you impose this constraint, then the set of things which satisfies them declines drastically. And the interesting thing is, you know, this is just you know, just an observation, which is probably of no use at all. But you know, this fixed prices is kind of an outcome. Suppose you're, you know, in an Edgeworth box. Suppose you want to distribute resources, you know, in an incentive compatible way.
Right.
Then you know, this Matt Jackson showed that the way to do it is actually to have fixed price trading.
Yes.
Fix the prices, and then given, you know, then preferences over this budget set are actually single peak.
Yes, exactly.
Yeah. So you get that for free.
Right.
You know, you
know.
No,
so you're absolutely right, Arnav. I mean, first of all, like Debashish also asked the question, right? What if you were to impose such constraints, like the amount of effort should be at least something, or in the case of Sprumont, should be exactly equal to something. Of course, in a single agent case, in a single agent case, perhaps that might not, the exactly equal to something might not be, unless I say expected effort must. So some sort of feasibility constraint.
I mean, there's no way you can get him to do it.
Right. So, but with multiple agents, that might be an interesting extension for sure. I mean, I'll have to think about, again, I've not gone there. I mean, whether that would, I mean, how these things would even replicate. But as you say, I mean, the class of mechanism is gonna be much smaller. So hopefully there is a general result over there. And yeah, I mean, the fixed price trading idea is fantastic. I mean, I was fascinated by that when I read that paper. That was pretty cool. And yes, you get moment you fix the price, yeah, you do get these single peak preferences. So one imagines that, yeah, that should be a natural place to start when you're thinking about single principal and multiple agents. So, but yeah, I hope again that all of these things are interesting extensions that we can explore.
Just one more point. I mean, this is,
yes,
very nice the way you do it. The other paper that I have seen, which tries to, actually examine the structure of an optimal contract in a model which is similar, is that paper by Moldovanu and who's that guy in Toronto? I mean, I'm just saying she, but I'm not sure. I think it appeared in the Review of Economic Studies. So you have single peak, you have single crossing preferences.
Okay.
And basically the planner is trying to maximize the expected something or the other. People, there is some parameter space. People have some single peak. It's not the same model because it's not an action. It's not an action model. I mean, I can see that your model is different, but they do have some. That's the only other paper we've seen where they've made at least in a I guess what I meant to say was there are lots of papers which look at optimal mechanism with money in quasi-linear, starting with Mars. But models, sort of models without money, which we might call voting models, there is relatively less. Even there is less work. The only one that I know actually is Moldovanu and whoever. Just some. Anyway, very nice paper.
Thank you,
Rene, and I'll send you some. I was just going to say by the as an aside, I'll send you something that we were writing on undominated strategies. So I'll send you that.
Okay, of course.
Nice talk, and I'll take your leave now. Actually.
All right. Thank you so much, Arunava. This is really appreciated. I mean, I didn't know about these papers, so I'll definitely have a look, and it would be interesting to see if I can incorporate them, at least as references for now. But yeah, please do send me the paper. I would love to read it. But thank you so much for your comments and your time.
Thanks.
Just can I add one point?
Yes, Sarvesh, please.
If that time is there. So for finding the optimal mechanism, you have explicitly assumed that the discontinuity can be at possibly k points.
Yes.
So one can think of a case or a condition, say on u or maybe on pi, such that even the optimal itself, even if you allow for many points at discontinuity, the optimal could be only for the finite point. So maybe it could be worth
yes. So for instance, I mean, I can relate to the delegation literature. So if you look at, let's say, the latest paper by Karthik et al. So over there, they do provide such conditions. So they in fact, they allow for stochastic mechanisms. So they are stronger in that sense. Their results are stronger in that sense. But they provide, like, I think 3 basic results on particular interval delegations, right? These intervals could be they coincide with something like the agent optimal mechanism or the take it or leave it mechanism. That's also a single interval, right, of contract. So they do offer those conditions. I mean, they are about typically about some sort of concavity of the utility function and log concavity of the distribution.
So if one borrows the conditions from there, then your assumption of k points is actually the implication that
so I mean it is exactly. So within that, if those assumptions are true, then the optimal mechanism will only have, let's say, 1 point of discontinuity.
1 point.
It cannot have more than 1 point. So yeah, you can potentially, there is a theorem one could prove. I mean, again, I mean, maybe there is a whole characterization of class of, let's say we fix the utility function and then try and characterize in terms of class of densities. But notice there are multiple things floating out. There is a utility function and the density.
True.
So
True.
the actual characterization can be fairly
very
complicated if
absolute,
you want to
absolute.
characterize. So, but you're right about that. Yes.
Thank you. Thank you.
Okay, so since we are out of time, so let's thank Rene and thank you very much. Nice talk. So very nice.
Thank you so much, Debashish. Really
Thank you, sir.
appreciate it.
So
Thank